Great, thank you. Good afternoon, everyone. Hope you had a good lunch, and I'll try not to put you to sleep after eating. So we're going to talk about deep learning for recommender systems. My name is Nick Pentreath. I'm ML Nick on Twitter and GitHub. I'm a principal engineer at IBM, where I work in the Code team, that is the Center for Open Source Data and AI Technologies. I focus on machine learning and AI. I'm an Apache Spark committer and PMC member, and I've written a fairly out-of-date book called Machine Learning with Spark. Just a little bit about Code before we kick off. It used to be called the Spark Technology Center when I joined, and we recently rebranded this team to Code. And our mission is purely an open source team and to enhance the end-to-end enterprise AI and machine learning lifecycle out in open source. So that encompasses Apache Spark and the surrounding ecosystem, Keras, TensorFlow, and other deep learning frameworks, the Python data stack, and a couple of projects that we've launched, the Fabric for Deep Learning and the Model Asset Exchange. So if you want to learn more about Max, I would encourage you to attend a talk a bit later at 3:20 p.m. by my colleagues. So today we'll give a little overview about recommenders, a little overview about deep learning, and then dive into where these two worlds meet and some of the latest advances in the research in this area. And then sort of wrap up with the challenges of this domain and the future directions of the research. So why do we really care about recommender systems? Well, they're probably one of the earliest and most commercially useful applications of machine learning, and certainly at scale. So pretty much all of us encounter a recommender system not just once, but many times per day. Every time you go to an e-commerce site using social networks, search engines, using movie or music streaming sites, mobile apps, all of those are driven by recommendations and personalization systems. And for many of these companies, it's a significant contributor to their bottom line. So for Amazon, the estimates can range up to 30 or 35% of their revenue is driven by the recommender engine. For companies like Netflix and music streaming, that can be as high as 70 or 80%. So it has significant value, and that's why it's important. So in a typical recommender system, we have two types of entities. The first is the user. Without a user interacting with your system, there is no recommendation or personalization. And the next is the item. Items can be many things. They can range from products, books, movies, through to pretty much anything that the user can interact with, including other users. And we have a lot of rich metadata attached to each of these entities. For users, you have the kind of demographic data as well as activity data. When were they last active? Are they new users? How long have they been around on the platform? And for items, that metadata is even richer. We have categories, tags, descriptions. We have rich content such as images, video, audio, and we also have activity data. How popular is that item? When was the last time that video was viewed? Perhaps how many likes, how many shares? So our system has to take into account all of this data and try and use that to make better recommendations. And the core piece of data that we really care about is events. So every time a user comes along and interacts with our system, they're telling us a little bit about their preferences. And most of the examples out there in literature and blog posts and whatnot that you'll find talk about explicit ratings, like movie ratings. But the overwhelming majority of the data that is actually available is in this implicit preference data. So if someone comes along and views a product page, that's a light indicator of preference. If they add something to their cart, that's a stronger indicator. And if they purchase it, it's a very strong indicator. But it still doesn't mean that they definitely like that product, because perhaps later on they actually didn't like it and returned it, but you never got a negative review, and maybe you didn't know about that return in your system. You would never actually know that they didn't like it. So it's all implicit, it's all indicating preference, but it's not an explicit rating. And we have to deal with that. And then attached to each event is a set of context. So the geolocation, time of day, what device they're using, if it's a kind of mobile app or web app. All of this has a role to play in how we make our recommendations, because you may want to show, for example, a different recommended movie if someone is at home in the evening versus if they are commuting to work or at work, for example. And then a recommender system prediction is not the normal, easy kind of machine learning model prediction of just making one classification. You actually have to score each and every item in your catalog, and each and every possible recommendation, and then you then need to rank it. So the entire act of predicting becomes quite complex. And finally, you have this well-known problem called the cold start problem, which is when you don't know anything about a user or an item. They have no history. So a new item gets added to your catalog. You have no historical interaction data. So typically you need to use some kind of baseline approach or the item content to try and make recommendations in those cases. And for new or unknown users, these are either completely new to your system or perhaps they're browsing anonymously or something like that. You again have no context, you have no historical interaction data. You might have some context data, but if they're anonymous, for example, that can be quite limited. So there's a couple of ways of dealing with that, and typically you'd either fall back to using item-to-item similarity or trying to represent the user as some aggregation of items as they move through a session. But later we'll see a few algorithmic techniques for trying to deal with this. So I won't spend too much time on deep learning. I think many of us are kind of familiar with it now, but it's been around for a long time in concept and rose to prominence in the kind of 50s and 60s. This is actually a perceptron machine. So that's what a multi-layer perceptron used to look like back in 1950s. And kind of fell out of favor and has had a recent resurgence due to bigger and better data, bigger and better hardware, and bigger and better algorithms. And it's led to state-of-the-art results in computer vision, natural language processing, and many other domains. So the modern neural networks or deep networks look like this: feed-forward networks, convolutional networks for domains such as image recognition, and more recently recurrent neural networks for sequences and time series. And a big driver of this success and the resurgence has been on the software side. So deep learning frameworks have this computation graph abstraction, which allows a lot of flexibility, automatic differentiation, GPU support. So it really allows you to come up with a lot of new flexible model architectures, try them out, and actually compute on them. So the key concept, especially in domains that are content-rich, is this idea of deep learning as feature extractor, automatic feature extraction. And this is the concept that we're going to see in many cases applied to recommendation models. So this is your typical layers of a convolutional network for image recognition. And the idea is that as you go deeper and deeper into the network, you gain this kind of higher and higher level feature extraction. So it starts off with some very kind of low-level image features, and then you start extracting areas of an image and kind of facial features, or a dog face, eyes, nose. And all of this is automated as part of the architecture. So we'll see how this applies to deep learning in a moment. Recommendations in a moment. But first, a brief tour of the history. So probably one of the first scalable recommendation models was the item-to-item collaborative filtering model by Amazon in sort of early 2000s. And then the Netflix prize in 2006 really led to a huge leap forward in research and techniques. So not dissimilar from the kind of ImageNet competition in image recognition. This created a very large standardized data set and a monetary incentive of $1 million to improve Netflix's model by 10%. So the resulting winner of that competition was an ensemble of literally hundreds of different models. But what did come to prominence were a few key techniques. And this really made matrix factorization the state of the art. There were a number of other techniques, but this became the core of many recommendation systems even today. It's worth pointing out that even then, neural networks in the form of restricted Boltzmann machines were one of the best single model performers. So deep learning in recommender systems actually does date back even to the Netflix prize. And that sort of was the status quo for a few years until factorization machines came out. And that was a generalization of this matrix factorization concept. And then more recently, we've seen this idea of deep learning as feature extractor start being applied to be combined with recommendation models and the traditional collaborative filtering. And one of the first was the deep content-based models, which we'll also talk about shortly. And then more recently, it's been gaining a huge amount of momentum with the Deep Learning for Recommender Systems workshop at the REXIS conference. So very briefly, again, Prelude is this matrix factorization, which is the de facto standard model today. And that's really about trying to take this user and item rating matrix and find a low-ranked representation of it that can then be used to make predictions. This works really well because there's efficient, scalable algorithms for solving it. It works well in practice, and prediction is really simple. So you just do a dot product between these vectors to make a prediction, or you find the cosine similarity between the item vectors to do item-to-item similarity. And it can handle this implicit data that I talked about before. So what's interesting and good news for us is that this can be easily recreated in these flexible deep learning frameworks. So for example, traditional matrix factorization in Keras looks something like that. So in a low-level framework like TensorFlow, you can use the weight matrices directly. In Keras, you can just use, or in Keras, you can use embeddings for users and items because they're really just categorical features, the IDs. You can use a dot product loss function, and then you just plug it into your standard Keras machinery, and away you go. But how do you handle this implicit data in this case? There's a few ways of doing it. You can either frame it as a kind of weighted regressional classification problem and apply the standard techniques with a weighting on the loss. You can frame it as a ranking problem and create custom ranking loss functions, which is shown on the right there. Or you can try to frame it as a classification problem and use the built-in machinery. Okay, so we'll dive into really trying to use deep learning as feature extraction for recommendations. And this was one of the earlier kind of use cases that was published, and certainly very important in the field of this research. So this was by an intern at Spotify at the time, and it was deep content-based music recommendations. So trying to use raw audio files to make recommendations. And in particular in the case of Cold Start, when you didn't have necessarily a play history for that particular track. So it works on audio spectrogram data and turns that into an image representation and then uses a pretty standard sort of convolutional neural network architecture. But what's interesting is that, as you can see on the right there, this CNN architecture is actually trained to predict the factor vector that comes from a collaborative filtering model. So it's trying to map the content to the item co-occurrence data and this interaction data that comes from the recommender system. So the idea there is that if you don't have a factor vector for an item yet, for example, it's a new item and it doesn't have any data, you can then run the raw audio data through this model, come out with a factor vector, and then use that to make predictions. And it came up with very natural and a playlist that looked really good. But the key here is that the models are still trained separately. So recently there's been a move to try and kind of combine different types of models and both traditional architectures, collaborative filtering architectures, deep architectures into one model and train them all together. So this is a very well-known paper, Widened Deep Learning from Google. And it's really trying to combine the strengths of traditional linear models, which are good at capturing low-order interaction features, and deep models, which are really good at automatically extracting high-level features. But the key here is that you actually have to, as a data scientist or the person doing the modeling, you have to specify which feature interactions to use. So there's still a lot of manual feature engineering that goes into this linear component. So can we do better than that? This is actually a really interesting paper which is not so well known, which I came across, called Deep FM. So I mentioned factorization machines briefly earlier. I could probably do an entire talk on factorization machines just by themselves. But the idea is really to take that matrix factorization idea and extend it to arbitrary side information, so that metadata, contextual data that comes along in this domain. And it factorizes arbitrary order interactions between all of those different variables. So your user IDs, your product IDs, or movie IDs, and all your contextual and metadata. So what's nice about this is that it takes away this manual feature engineering effort that you have to do and will automatically find the interactions and combinations that are important. So DeepFM looks very similar to the wide and deep model and was naturally inspired by it. And it tries to combine the strengths of the FM layer, which is in the sort of top left there, for doing this automatic feature extraction for low order feature interactions with a deep model which does the sort of higher order interactions and nonlinear interactions. And they share an embedding layer, and the model is trained all together. And as you can see at the bottom, at least according to the paper, they achieve better results than all the other models, including wide and deep learning. So I've mentioned embeddings a little bit, and this is really a key part of most kind of recommendation engines. If you think about that, the factor vectors that come from matrix factorization models, those are exactly just embeddings, very similar to your RNN text models or whatever the case may be, word to vec. And this is some research by Criteo, who released this content to vec paper. And this is really about trying to build a modular architecture or set of architectures for different types of content and different types of metadata. So you might have an image embedding module, which will typically be a pre-trained ImageNet model, for example. You'll have a text embedding module, which could be word to vec, could be even bag of words, but typically CNN, RNN models. And then you have this collaborative filtering embedding model, which is a typical matrix factorization. And the key idea here is then to use those as pre-trained models for effectively doing transfer learning in the recommender domain. So in images, you might do transfer learning by starting with pre-trained weights and then doing classification on your own images. Here, you'll do transfer learning by starting with those pre-trained embeddings and trying to learn perhaps ratings on your own data set, or perhaps, in this case, they had a similarity metric between items. So this is one of the first steps to this concept of transfer learning applied to recommendation domain. So one of the really exciting new areas in this space is session-based recommendation. So the cold start problem is particularly pertinent when you have a new user coming along, or an anonymous user, and you know nothing about them. You have very little even contextual data to work from. But what you do have is an evolving data set of what they're doing in the session. So if you think about that session, that user session, as the set of IDs or the sequence of IDs that they are product IDs or movie IDs or whatever the case may be that they're interacting with, then that sequence can be thought of in much the same way as a time series or a piece of text. And we know that RNNs have been really successful in modeling these domains. So a couple of years ago, this was a paper that tried to apply these advances in sequence modeling to recommendation over user sessions. So it looks very similar to your standard RNN with a bunch of GRU layers, but there are a couple of domain-specific adaptations that are required. So one of the key things is that ranking losses were added. So instead of just using a classification loss or mean squared error, or whatever the case may be, they came up with particular ranking losses. Negative item sampling becomes important in this case because in order to compute the ranking loss, you have to have the set of positive examples. So these are the items that a user did interact with, but you also have to have a set of assumed negative examples, ones that they didn't, and then you assume that those should be ranked less highly than the positive ones. And typically, you are dealing with a domain where you have a significantly large set of candidate items. So you don't want to necessarily use all of them as negatives. You want to sample from that. And they took it a step further by doing sampling per mini batch. So instead of sampling from the entire candidate set at each sort of phase, they would sample from just the candidate items in the mini batch. So this sped up processing. and training time. And they also could make use of parallel mini-batch processing. So in many sequence modeling tasks, you can't necessarily make the assumption of independence between sequences, but in user sessions, you probably can get away with that. Each session is probably going to be independent of another user session. So that's exactly what they did. They just processed them in parallel. So they reported a pretty big accuracy gain over other baselines in this domain, so session-based data sets. And that was the kind of first version of this model, which is not using any of this other rich data that we talked about, this content data or context. So one of the extensions to this was contextual-based models. So the idea here is really to take that original RNN model and inject the context data. So, as you go into the current item, you model based on the current context, and then given all of that and the next context, you make a prediction about what the next item is going to be. And that resulted in a small improvement over that simple RNN baseline. So we've gone through a bit of a whirlwind tour about some of the more recent advances in applying deep learning to recommendations and recommender models. There are many other papers, but we can't really go through all of them. But some of the challenges that you face in this domain are that you typically deal with a huge amount of data and a large dimensionality of that data. So you might have tens of millions of users, hundreds of millions, even billions if you're a large social network. And again, hundreds of thousands, millions, even hundreds of millions of products. And that data set is extremely sparse. So typically, deep learning frameworks, for example, haven't until recently dealt very well with sparsity. They're really optimized for dense domains like image classification. But embeddings and compact representation, compression, quantization, and these kind of techniques become increasingly important for this domain. You have to combine the session content, contextual data. So you have this multimodal nature of the data, and you have to combine all of that. And as we saw before, model serving is tricky. It's a ranking problem, and it's not a simple prediction problem. It's computationally expensive, and you have to find ways of ranking large numbers of items. Metrics are important, and in many domains, the machine learning metric that you might care about doesn't necessarily correlate to the business metric that you care about. And this is probably even more the case in recommenders. So, this is kind of shown by Netflix moving away from just the root mean squared error as a metric, because it had very little to do, whether you could predict ratings well had very little to do with actual, a business success, and had very little to do with increasing user activity. So ranking metrics do a better job, but certainly it's difficult to actually map how well your model is doing at predicting to how well it does in increasing the kind of user behavior that you care about. Despite some interesting data sets out there, there is certainly a lack of standardized, open, large-scale data sets, and in particular ones that have both content, context, metadata, and time data, so this sort of allowing this kind of session-based data. So there are a few out there, but it's still fairly limited. And then when it comes to evaluation, I think this applies to most deep learning sort of applications. What's your baselines? We've seen a lot of noise about the new deep learning model doing very well and beating baselines. But then if you go back and actually create a really good baseline and tune it appropriately, you see that performance gap narrows. And this certainly happened even with the RNN for recommender models, for session-based models that we saw. They claim 20 to 30% increases in performance. But if you go and you calibrate a nearest neighbor model correctly and you make a good baseline nearest neighbor model, it actually turns out that performance gap is almost eliminated. So I think we just need to, as potential users of these models, just be careful of these evaluations and baselines. So some of the future directions in this space, I mentioned the RNN and session-based models. This is a big focus for research currently. So looking at trying to generalize those, obviously adding more ways of modeling context and content data, cross-session models, hierarchical models for dealing with both the long-term and the short-term history of a user session, how to combine those sequence and historical models and your kind of your historical collaborative filtering models together, improving embeddings, and dealing with application at scale. So I've mentioned the scalability issues, but certainly dimensionality reduction techniques, quantization, and compression are all really important, particularly at serving time. So to sum up, I believe deep learning for recommenders is just getting started again, because it does date back to Netflix. There's been a massive increase in interest, research papers. I think the industry applications are yet to come and will start filtering. But it's worth pointing out that a lot of these gains are, in terms of metrics or accuracy or model performance, fairly incremental. So if you look at a few percent increase, it doesn't sound like a lot. But if you're in the ad targeting domain, product recommendations, increasing your performance of your model predictions by a few percent can actually result in significant increases in revenue. So we shouldn't be worried that we're not having huge leaps in performance like you had in image recognition. This still has a lot of monetary value and economic value. So what's nice is, because we're using these deep learning techniques from other domains, as those domains get better and better, and as they release more state-of-the-art results, we can just fold them in, using these flexible architectures. And there's been a recent open source libraries appearing, such as Spotlight for PyTorch. I'd recommend you check it out. And the Deep Learning for Recommender Systems workshop has really been where a lot of the new research has come out, and that's going to be happening again in October this year, and the papers will probably be announced shortly. So if you want to see what's going to happen in this space in the near future, keep your eye on that. So I'd like to thank you very much. Encourage you to go and check out codea.org. And as I said, if you're interested in the model asset exchange and hearing more about that, Fred Rice and Vijay will be talking about that at 3:20 in the AI track. Thanks very much. I think we've got time for one or two questions, if there are any.
Do you have any working examples of any of the deep learning models?
So there are a couple of links here, and some of them have code snippets. I will publish the slides, and I'll put them up on Twitter and SlideShare. But some of them have code snippets. Definitely worth checking out. As I said, Spotlight, which is it's on GitHub. Spotlight is a PyTorch framework that incorporates some of these both collaborative filtering-based models as well as the session-based models. So it's still a fairly new space from the framework perspective. Spotlight is one that I know. I'm sure there's certainly others floating around, but they're mostly examples and code snippets and not necessarily a fully fledged framework that you can use.
One more question. Hey. So I'm not in this field, so I'm not sure how much of a concern this usually is, but usually when you introduce deep learning to an area, you care about interpretability. Is there any equivalent concern here? Like if you start using deep learning for recommendation, how much actionable information can you extract, like in terms of getting new products that people typically like?
So
basically, can you infer something from the model itself? Saying, so if you're looking for new products that people might be interested in, is it easy to do using these techniques versus previous techniques?
So are you talking about ease of just computing predictions or explainability of what the model is doing?
Explainability, basically. So, but in particular, like if you as a business who is interested in using recommendation systems, you want to figure out like what is a new interesting product that people would be probably likely to be interested in. Like if the model itself is opaque, it might be a little bit harder to.
Okay, given a set of users, you want to just compute the top products that they might want that you might want to send out to a newsletter or something like that. Yeah, I mean it's not dissimilar from how you do it with a collaborative filtering model. So if you've got a bunch of factor vectors, you've got a user and an item matrix effectively. You take that for each user, you would then compute the top recommendation. So it's a very computationally intensive process. And with a deep learning-based model, it turns out to be pretty much the same process. It's just more computationally expensive. So, you know, if you think of the users and the items as embeddings in a deep learning model, then your basic version is exactly the same as collaborative filtering, and you to do the same computation. But if you now want to fold in all the extra metadata that you have about the users and maybe the context and the products, for example, then they would all just be part of that feature vector that gets fed into the model. So it's just more computation, but the concept of doing it is the same. You know, for each user, you have to score each and every model, each and every product, create a ranked list, top 10, top 20. So, and you know, you can batch things up and use linear, use matrix operations instead of matrix vector operations to speed things up, but it's still a very computationally intensive thing. So for large item sets, typically you want to use some dimensionality reduction technique, or locality sensitive hashing is a very common technique to try and pre-compute the LSH signatures for each of your items, and then instead of scoring your entire item set for each user, you would score a significantly smaller candidate set for each user. But ultimately, this is typically, if you want to do this you want to do it in a big batch run, it's a good use case for a distributed system like Spark or something like that to try and speed up that computation.
All right, so unfortunately we are out of time, but Nick will be available in the back of the room or outside.
Yeah.
If you guys want to mob him with questions. All right, great. Thank you, everybody. 10-minute break.